In this video, I'll talk about research designs. So, how do you set up your study to test a certain hypothesis you have in mind? Let's say you have some hypothesis, then you have some constructs in mind, and you thought of a way to quantify them. How are we going to then set up the study to test the hypothesis? If you have only two variables, one predictor, one outcome, or one independent variable and one dependent variable, and let's say the independent variable is something that we manipulate or control, which we usually do in groups. Like we have, for example, one group that got some treatment condition and one group that's a control group, or maybe comparing two different groups of people. There are two things you can do. You have the independent groups design where we basically look at two different groups that are different people. For example, we give one an intervention. Maybe we let them go to a summer camp to meet people. And another group we don't give it intervention, to maybe let them be on a wait list or not do anything special for a week. Then after the intervention, we compare them on some other variables, maybe their happiness. Another thing we can do within groups design, then we look at the same subjects over time. So maybe we measure people and their happiness before summer camp and after summer camp to see if they become more happy over that time. Now, if you have more than two variables, and especially if you have more than one predictor, so more than one independent variable, we can have more complicated designs. For example, we can have a design where we have two categorical predictors or independent variables. We call it a factorial designs. So now we might have, for example, both a control and a treatment condition, and we look at men and women. And we want to see if those things interact. Maybe the treatment only works for men, but not for women. That might be useful to see. Or we might have a mixed design where we have one variable that is at the within person level, one variable that is at the between person level. For example, we might have a measurement before and after the summer camp, and we also have a control and a treatment group. And so maybe the treatment group goes to the summer camp, the control group does not, and we measure them both at the same time, before and after the week, see if they change. This is what we call a mixed design. So here's an example. Here I have a study. I have an hypothesis, and I think that musical therapy will make hamsters happy. Participants, but let's say they're cute hamsters. All right, so this is my theory. I have here on the left a sad hamster. Then that hamster listens to really nice music, and now it's a happy hamster. Right, and I think this is causal, because that hamster listened to music, that hamster became happy. Right, so how do I test that? Well, here, let's say that I have more than just hamsters, right? Here I have two groups. Maybe one group, I let them listen to music. Another group, I don't let them listen to music. And I measure their happiness afterwards. And I might get something like this. So you see here that this experimental group is actually quite a bit higher than the control group, right? Oh, it's a terrible drawing, okay. It's a little bit higher. This is a bit more lower, right? But there's also quite some overlap here still, right? So these are all bits around the same scores, but we see that the general experimental group is just a little bit higher. In this case, we can do an analysis. You might have learned this before. We can do an independent group samples t-test, and we get some results. So just tell us t. Test statistic. That's a statistic which is basically standardizing the difference between the two means. With the degrees of freedom, something we'll talk about later, but it's basically the number of free elements in calculating this difference, the variance, equals some value. But that's not that important. What's important is this thing here, the p-value. The p-value is a number that quantifies how likely would this effect be. So there's a difference of 1.48, the standardized difference. How likely would that be if there was actually no difference between the two groups? A bit more precise, actually, p-value is the probability that if there is no difference between the groups, you would observe such a difference, such a t-value of 1.48, or more extreme, or even more bigger differences. It's a bit weird, but that's the interpretation of it. In this case, p is 0.16, and we usually use an alpha level of 0.05 or 0.01, depending on how conservative you want to be. Basically saying that, okay, we deem something significant if the p-value is below this alpha level. That's in this case not the case, so we would not term this a significant difference. So we see, yes, sure, there is a difference, but it could be due to chance alone. Now another thing we can do is measure the same subjects over time. So now we measure subjects before an intervention and after intervention. We give all these participants, right, the intervention. So these are only the participants from the experimental group. And they're the same, right? So we have the bird here, we have the giraffe here, we have this bird here, we have this orca there. And we can see that all these lines are going up a bit. Right? So we see that on average the change is actually positive. And now we can actually look again at how these two groups differ, but we take into account that they're the same people. So what we're actually looking is how the differences between these two observations, what their average is, and if that's different from 0. In this case here, this t-value quantifies standardized difference again between the two groups. And we look at, is that different from 0? And we find a p-value that is very low, indicating that if there was no effect of this intervention, we would not expect this number to occur. So it's an interesting finding. We would call it significant. The only problem is, this is nice, but do we really know if the intervention worked here? Because there's more things that happened here. Time also passed. So we're not varying only the intervention, we're also varying time. Maybe people just in general a bit happier. Maybe we measured people first in one particular week where other things were happening in the world and people were sadder than usual. And the week after, where we measured them again, for some other reason they were happier, regardless of the intervention. We don't know. So we can't say, okay, this effect, this is really due to the intervention. We don't know this, right? It could be that if there was no intervention, so let's say these did not go to summer camp, they just sat at home, they would have still gone up in their happiness just because of some other reason, right? Maybe it was bad weather the week before and it was now nice weather, and they're happier. But this is where the mixed design comes in. And this is a form of a factorial design where you have both a within person and a between person variable. In this case, we split the sample up between two conditions, control and experimental, and we measure them both before and after intervention. So now we have a measurement before and after the intervention. Let's say the experimental group goes to a camp and the control group does not. And we also have separation between two groups. Right? So one goes to camp, the other does not. We measure before that camp and after the camp. Or before that they don't do anything for a week and after they don't do anything for a week. What do we see now? Now we see that in general, these people went up in the experimental condition, but in the control condition not much changed. They're all about the same. Right? Some people went up and down a bit, but the effect is on average not different. That's what we call a mixed design, where we have in this case a within group predictor and a between group predictor, which is condition. And it gives us quite some results actually. You see here we have more results than we usually had. We have a main effect for both the conditions. So that means the effect of one predictor ignoring the other predictor. In this case, we see that actually there does not seem to be a main effect on condition alone. So that means that if you were in experimental condition, you are not necessarily more happy than being in a control condition. That's not really a problem because half of these measures were before the intervention, so that was just a random sample at that point. We see an effect of measurement, a very small one, and we see an interaction. The interaction here, that's the one we're interested in. The interaction looks at, is there a difference in the effect over time in the control condition compared to the experimental condition? And that's the one our hypothesis would be at in this case. We would we do not necessarily expect a main effect for measurement because we still have the control condition. we want to find the significant interaction effect. And here we find it, right? So we see, okay, the relationship over time is different between the control and the experimental condition, right? And that is actually in line with our hypothesis. We expect that a control condition where nothing happens, they stay just as happy as normal, and in experimental condition, they would actually go up. So here's an example of the note-taking study we discussed earlier in this course, where we also see a significant interaction. There's only difference on performance in one of the conditions, in this case in the conceptual condition, but not in the factual condition. So that was the main finding here, this significant interaction here. I'll end this video with a discussion of things that might impact your validity beyond the research design. The first is confounders. So a confounder is a variable that affects the outcome instead of the intended predictors. It's a variable that you did not include in your analysis. If you did include it, you call it a covariate instead. So a confounder could be something you did not take into account. It's actually explaining the result you found. And so for example, let's say we send an experimental condition on a camp to be around people, to be less lonely, and a control condition we don't send on the camp. But maybe the camp is in a nice place, like let's say Thailand, right? And it could be that people get happier participants just because they're in Thailand rather than being around people, right? Or maybe the different aspects of the camp that are impacting with its results than only being around people. Artifacts are other reasons why your results might be as they are, that are not due to the measurement or the design. For example, you could have some form of selection bias in the data. Maybe your sample is not really a random sample, but rather a very specific sample from the population, like people that have clinical depression, for example, or people that are enrolled in a very large or very prestigious university. Those people might differ in some ways from other people, and also the selection itself might actually lead to an effector curve. This is a pretty interesting thing. It's a bit hard to explain. But for example, suppose you have a sample from people from Harvard University or like a Ivy League university in America. And in a university like that, you can only really get in if you are really, really, really good academically, like have top tier grades, really, really good. Or on a sports fellowship, like if you're like Olympic athlete level athlete, right? Like a super good American football player, for example. You still need to be good academically, but not as good as the other people. In this case, if you look in a sample of people from Harvard, and we see that the person is in there because of a sports fellowship, because the person is very good athletically, we might be able to predict that, okay, maybe that person is not as good academically as the other people that are in Harvard, simply because the other people were selected due to their academic skills, not their athletic skills. So that actually creates an effect between two things that might not have an effect in the real world. Non-random missing data. So this means that if people are not responding to the questionnaire for important reasons. Say we are measuring the effect of loneliness on happiness, but maybe people that are very happy, they are not responding to the questionnaire because they're so happy they don't have time, right? Or maybe we are measuring the effect of an intervention, like a government campaign, on people using illegal substances, like vaping in Singapore, for example. And it could be that people that are using illegal substances don't want to say that they're using illegal substances, so they're just not giving any response. In that case, it's going to massively impact the study, and you might completely miss out on the effect that we're interested in. Regression to the mean. This is a very interesting effect as well. Regression to the mean tends to happen if you have extreme scores. They always tend to be less extreme in the second measurement. For example, I throw dice, and I throw a 1 or a 6, or 6, the most extreme scores. My average throw is 3.5. I expect to throw on average 3.5. It means the next time I throw, I expect to throw a more reasonable score. The 1 and 6 are very extreme. There's a 2 out of 6 probability that I throw 1 of 6. There's a 4 out of 6 probability that I throw something closer to the mean, like a 2, a 3, a 4, or a 5. I'm more likely to throw like this score close to the mean. And this is something that happens in psychology as well quite often. So maybe we had a selection of subjects at a certain point in time where they had very extreme scores. And we expect them to just become a bit more average over time already. If maybe we had a selection of patients entering clinical practice at their worst point in time, and they might already go a bit back to baseline. Another effect that could definitely impact your results is experimental bias. So it could be that you're unconsciously influencing the outcome. If you know that a person is in a certain condition, you might treat that person differently, even if you don't intend so, because you think that the person should have a different outcome. So maybe if you're one of the people in the camp, you're going to make those people extra happy because you think that should lead happiness being together with people. Demand characteristics of participants might actually also change their behavior knowing that they're in a study. It could be that when a participant is in a study, they might respond in a way that they normally would not do. Placebo effects. So placebo effect means that participants change their behavior because they actually believe they're receiving treatment. They think, okay, I got a psychological therapy, for example, so I should be feeling better, even though it's not based on a real theory, for example. And that tends to happen as well. In medicine, this is very common, that people get a dose of a nonsense pill, but they believe it works, and actually that will give some effects as well. Right, so these are some big concerns to validity and to, that I don't really have time to discuss in more detail in this course. Of course, they're discussed in other courses and in textbook as well. So if you're interested in that, you can read more about it as well.